Alright, this is my solar tracker. I finished the hardware portion of it. It's constructed of three pieces. The backboard, the spine, and the pedestal. The backboard is attached to the spine via gate hinges, and there's three of them. Okay. The solar panels attached to the backboard via these T-slot aluminum rails that I've attached to the backboard. The reason I did this was if I ever want to add a more powerful solar panel, I can just simply unbolt these, slide them off the rail, and then slide the larger solar panel onto it. But for now, the panels I have are sufficient. They're, as you can see, I have two panels. Each one is 25 watts, and I will attach them in parallel so that it'll plug into a solar charge controller to my 12 volt 7.2 amp hour deep cycle battery. Not sure how long it will take to charge the battery, so that is yet to be tested. Alright, this is a dual axis tracker. Right now I've only automated the one axis, the axis that will control the tracking of the sun as it moves in the right ascension. The declination is manually adjusted because the sun, the maximum elevation the sun will reach is 65 degrees, and it doesn't change over short periods of time drastically. So from winter solstice, the sun's maximum height is approximately 15 degrees in my area. At summer solstice, the sun's highest elevation is 65 degrees. Okay, and what I'll do, I'll show you here, is simply pull out this pin, rotate the spine to the appropriate angle in increments of 15 degrees, and then lock it in place. Alright, so pretty straightforward, simple, and it works. In the future, I may elect to add a second linear actuator here to automate that function, but for now I'm okay with just changing the pivot, pulling the pin out, and then locking it back in place once a month. It should be good enough. So I'm pretty happy with my design. The backboard pivots, like I said, on these hinges, and is controlled by the linear actuator. When the actuator is fully retracted, the backboard should be about here, which I think I measured was about 30 degrees. So that's as far back pointing east it can go. I could have made it the angle a lot smaller if I had gone with a longer or a linear actuator with a longer arm, but I elected for a more compact design, so that's why I went with the 6-inch. So the panel will actually rotate from 30 degrees to I guess this would be 150 degrees? Yeah. So that's not bad. So as the sun moves across the sky, the panels will rotate. Actually, it's by about 120 degrees rotation, which is enough for what I'm looking for. So that's it for the hardware portion of the solar tracker. It's off to the electronics now. Alright, I think I'm finished prototyping my least electronic part of the solar tracker. The source code I spent last weekend several late nights on the weekend coding up the source code, and refining it a little bit over the week. It was lots of fun. The Arduino IDE, I mean, it's not as fancy and feature full like you'd see in maybe GCC or Visual Studio, but it works well enough. There are some weirdness in the IDE. I wasn't able to implement some of the things I wanted to implement, but that's okay. The basic functionality of the solar tracker works. I haven't plugged it into the linear actuator yet. That'll come tomorrow, hopefully, fingers crossed. And I'll include this in this video. I'll just do some editing and provide a full video instead of publishing separate videos. Okay, let's describe what I've done here. So the components I have here is Arduino Nano, and I chose this over the Mini that I have. The Mini doesn't retain the sketch that I've downloaded when it powers off. I don't know why. I think there might be a bootloader issue or there's a bug, and I haven't figured that one out yet. So in the meantime, I've decided to go to the Nano because this will power up, and the sketch that I download is retained in memory. So all I have to do is just power it up, not plug it into a computer and upload the sketch. I won't have to do that. And this is the main driver, which I've coded, that will drive the linear actuator, which will cause the solar tracker to follow the sun as it moves across the sky. How I do that is I compute the sun position based on time, and to get the time, I have a DS3231 clock module with a little button battery that will retain the time, and I've coded it in such a way that, or I programmed it in such a way that it has the UTC instead of the local time, because the sun position function requires UTC time, not local time. And I also feed the sun position function the latitude longitude for my area. Okay, this is a 1306 OLED device. These two came, well, actually the Nano, the clock, and the LED came as a kit. I think the vendor was called Way In Top. So far it seems to work fine. I don't know what the power consumption is on this whole setup, so I've actually ordered a USB power meter, and so that should be coming in later on this week or early next week, and I'm hoping to plug it in and see what power consumption is required for this thing. I'm a little bit concerned that this will drain a 9-volt battery too quickly, and that won't be a viable option. So I have to think of something different. And then this is a dual channel relay. This is where I will plug in the linear actuator, and this is where this will drive the linear actuator, which will then cause the solar tracker to track the sun. Okay, let's plug this in, and I can demonstrate to you how it works. And I'll show you the code later on here. So when I plug it in, the code then does a setup, and what it does is it doesn't know where the linear actuator. Let's say there's a power failure. The linear actuator is partially extended or fully extended. So I immediately have it drive the this channel here, or this relay here, and that will retract the linear actuator arm, and then set the backboard so that the solar panel is facing east automatically. What's happening right now is, because of the time, it's 58 minutes UTC, the sun is still above the horizon. So now it's extending the arm. You can see by the red light here, extending the arm so that it's causing the solar panel to face the sun. Now the sun is about to set, so that's why this is not outside. being tested right now. I'm gonna, hopefully tomorrow, if it's sunny, I will set this up and do a time lapse of it, and I'll just append it to this video, so it's just one big video there, and so it's done. Okay, you can see on the LED, you can see the date. Okay, you can see the time, which is UTC, and I've also displaying the sun position. The elevation is right now 14 degrees, and the azimuth is 269 degrees. Originally, the source code that came with this little kit here, I downloaded it from the internet. The vendor, I think I already set that as way in top. It worked, and it displayed the temperature, which I don't really need for this particular setup here. But I wanted to display the elevation and azimuth. So I couldn't get it to display both temperature and elevation azimuth on two separate lines underneath the time. I don't know why. It was really weird. So there's some weirdness with the Arduino coding IDE, but I didn't have time to figure it out. I was more concerned with making sure my code fit within the Arduino memory and program space. Unlike desktops, you're limited to, on this particular device, 32 kilobytes of program space and 2 kilobytes of memory. So you have to be quite frugal, which is, and I'm amazed I'm able to do what I'm doing on such a small little device, which is pretty cool. Okay, so I don't know what the power consumption of this whole setup is. I actually ordered a power meter, USB power meter from Amazon, so that's coming in later this week or earlier next week, and I'll use it to figure out how much power is being consumed by this whole setup. If it's too much, it's more than, and I suspect it's probably more than a 9-volt can handle for, let's say, a month. I suspect it'll probably be 3-4 days that'll just drain a 9-volt battery. So I'm going to have to find a different solution. And I think what I'm going to do is I'm going to get a buck converter and then convert the 12-volt coming out of the battery that's being charged by the solar panels, and then changing it to 5 volts and then powering up the Nano with that 5 volt. And that should be more than adequate, and that'll last forever, because the battery will be constantly being recharged by the solar panels during the day, and it'll be the deep cycle battery. I mean, it's a small battery, but it's the one I'm planning to get is a 7.2 amps hour battery, so it should be more than sufficient to keep this thing running indefinitely, or at least longer than a 9-volt battery. Now, to reduce the power consumption, I added a third button. It's on the left here. Before, there's only 2 buttons. I added the third button, and that turns off the display, and that should reduce the power consumed. That actually puts the display to sleep, and I can power it back up. And I have it on the buzzer clicks on when that's activated, because as you noticed, when the time displays, it doesn't display every second. It's displaying every 5 seconds. I've got the Arduino, the code, it's basically pulling in a loop, and so what I've done is I put in a delay so that it's the sun position function is called every 5 seconds. And because I don't really need to do real-time calculations instantaneously for this device, because the sun's not moving across the sky that quickly. So 5 seconds, I might even bump it up to a minute. But by doing that, if I have to activate these buttons, I have to wait, and so I have to hold it down, and I don't know how long to hold it down, so that's why I made the buzzer click on when the button is activated, and is actually received by the program. The second button is used to set the calendar and the time. And the third button here, this button, will actually increment the fields of either the calendar or the time. And let me show you here. So I'll just press that. Hopefully that works. The buttons are kind of finicky. They're not the greatest buttons. Yeah, see. Okay, so the day is flashing. So I could press the third button here to change the day, and then the calendar year, and the month, and and the day. Okay. Now, when the original code, these dates, when they flashed or when you were editing them, they weren't properly aligned, and so it was glitchy, and so I had to fix that. And here's the time. So hour, minutes, and seconds. Well, the seconds, there's no way to change the seconds. The seconds just reset to 0 after you've finished with the minutes, which is okay with me. I mean, this thing doesn't need to be that accurate for my purpose. Okay, so I think that's it. Here's the power, so I'm going to plug this into a 12 volt. And I still need to connect the leads from the linear actuator to the middle of each of these channels. Okay, the left terminal here of each relay is connected to the positive, and then the black wires here are connected to the right terminals of each relay. That's the negative. Now I don't know if I've got this properly assigned, whether this is going to be the retraction and this is going to be the extension of the linear actuator. I'll know tomorrow when I try it. If that is reversed, then I just switch the leads, and Bob's your uncle. Hopefully, fingers crossed. All right. I think that's it. Let's go through the code quickly. All right, hopefully this is working. This is the first time I'm trying the Xbox game bar. It's recording the Arduino IDE, and I'm just going to go through the code quickly for you guys here. Like I said, this code was originally downloaded from the Way In Top website. They provided this for those who purchased their clock Arduino kit, and I've made many modifications here. So let's scroll down here. Well, let's actually, sorry. Let's go to the setup. Okay, so I'm setting up the pins on the Arduino that are connected to the clock module, the relay, and the LED. Okay, along with the buttons as well as the buzzer. Okay, here I'm calling the function to retract the linear actuator when the unit is powered up. I do some, this actually came with the original code, and it's basically setting up the display. Again, this is all part of the code that came from Way In Top, which I'm really helpful to get me started. Otherwise, it would have taken me for a lot longer to actually get this up and running. But I'll scroll down to the loop function. So here's my loop function, and basically it's checking to see if the buttons have been depressed. Again, this came from the original source code. And at the very end, after that, I call the sun position function. Now this I pulled off of Stack Overflow, and it was quite helpful. I didn't actually have to code it myself. And I'll go to this function here just to show you. So I'm passing in the year, and in this case it's just the last two digits of the year. So it's this is 2020, so I'm passing in 20, the month, the day, again integers, the hour, the minutes and seconds, and this is UTC time, and then the latitude, longitude of my position here. Okay, and these are required because we need to calculate the local equatorial coordinates of the sun. Okay, and those coordinates are well, there's two terms. In celestial coordinates, you call them declination, right ascension, or in the other form, it's called elevation and azimuth. Both are expressed as degrees, though. Okay, and you can see the code here. Scroll here. It's actually quite complicated. This was actually taken from a paper from I can't remember the fellow's name. I'll have to look that up. Yeah, it was provided, and there was a bug in his paper, his algorithm, which was corrected by him, and people have implemented it, and thankfully provided it on the internet, so which saved me a lot of time. And so the function returns back the equatorial coordinates, which I called sun, stored in a variable called sun, and I pull the elevation and azimuth from that. And then I pass that, well, the elevation and azimuth are global variables, which are then used to update the display. And I have some debugging print statements here. I've turned it off. So, and then we call the function slew, and let's go to that function. And it's here where I take the position of the sun. I also take the current arm length, and I figure out how much to adjust the arm length on the linear actuator to get the solar panel to point at the sun at that particular moment. So I check to see if the sun declination is less than 0. If it is, basically I then check to see if the arm has been fully retracted or not. If it hasn't, then it will fully retract it. Otherwise, I then calculate the angle of the geometry of the backboard or the solar panel with respect to the spine on the solar tracker. Okay, and then I then check the right ascension, or in this case the azimuth, and see if the azimuth, and this is if it's within 0, greater than 0, or less than 90. What that means is then the sun is rising. It's rising behind the solar tracker. Okay, and if that is the case, and that will be the case in between the spring equinox and the autumnal equinox, then I basically take the angle of the backboard and spine and compare it with the declination, and then adjust the linear actuator so it matches. Okay, now and I do the same for when the sun is setting. So if it's setting at 90 degrees or 270 degrees, then I also do the same there as well. Now if it's not, and the sun is between 90 degrees and 270 degrees, then I use the right ascension to adjust the angle of the backboard. Okay, so and I haven't tested this with the hardware yet. I've just basically gone out and just looked at where the sun is, just using my thumb,
and just like, okay, I can see from where the sun is, it's roughly, let's say, 145 degrees, and the altitude is, or the elevation is approximately, let's say, 30 degrees. Then I look at the sun position from the Arduino, see what it's calculated, and I can say, yeah, that matches. So we're good in that respect, in that the sun position is being calculated correctly. Whether the arm is being set correctly is another story, and that's why I need to do the live test with the solar tracker, because that's all been parameterized. Now, the linear actuator that I have does not have an encoder. Ones with encoders are a lot more expensive, and so I opted for being frugal. In hindsight, maybe I should have gone with and paid a little bit more for one with an encoder, but this actually, I think, will work because I've calibrated, or I've measured the speed of the linear actuator going from fully retracted to fully extended. And from my measurements, it looks like it's 4.5 millimeters per second, which is off by the manufacturer's specification of 5.7 millimeters per second. So I may need to recalibrate this because when I did the measurements, it was without the solar panels attached to the backboard. And they add a bit of weight, and so the linear actuator may be a little bit slower. But I'll determine that, and I can always adjust these afterwards. The stroke length of the linear actuator, again, is specified 150 millimeters by the manufacturer. If it's out by a couple of millimeters, I don't care. And I don't expect it to be out by that much. Maybe a couple of millimeters, that's okay. There's the retracted length of the actuator and the fully extended length of the actuator. The piston radius is the radius, how do I describe this? The distance from the center of the hinge pin to the center of the angle bracket pin on the backboard where the linear actuator arm is connected to. That helps me determine the angle of the geometry, or so I can calculate the trigonometry of the solar tracker, the spine to the backboard. And then there's an angle offset. Now, because with that angle bracket for the linear actuator on the backboard, I had to measure what the angle offset was to the backboard so that the solar panel setting was correct. Here's the spine length, I measured that, and then the update frequency in milliseconds. So the calculations that I'm doing in the Arduino is taking about 1 second. And so if I add another 4 seconds to the delay, that's a total of 5 seconds for each update, querying the sun, or querying for the sun position. So I can change this and increase this, and I think I will. It'll depend on what the power meter will say in terms of the power consumption of this whole device. And then the update difference in degrees. So if there's a change by 2.5 degrees in the sun position, then that's when the relay will be activated and the arm on the linear actuator will extend. Now I can increase this as well, 2.5 degrees. I think what I was observing was that the relays were turning on, I think every, I shouldn't say, it was quite a long time before they were activating. But I might increase this to like 5 degrees. I mean, I don't need it to update that often, because the solar efficiency of the panels are such that if it's 15 degrees off center, we're still getting 97% efficiency in the solar panels. Even at 30 degrees, the solar efficiency is 88%, which is still pretty decent. It's only when you get more than 30 degrees, then that's when the efficiency starts to drop off. So we've got a lot of latitude here uh, uh, for doing the updates, and so I may decide to increase this. What else can I show you? I think that's pretty much it. Let's see, this is the retract linear actuator, and you can see I'm just basically setting the pins on the relay to high, and then I set it to low. That will actually retract, that will start the retraction going. Then I calculate the time, and actually that's a mistake. I should actually calculate this time before I set it to low. And then there's a delay, so then the pin, the retraction pin on the Arduino stays on for that amount of time, and then it's set back to high, and then that turns off. But this, I should actually compute this way before that. There we go. Okay. And then the set the linear actuator. This is where it does the extending the arm so that it can track the sun. And I'm just wondering if I have the same issue here. No, I don't. I calculate the time beforehand. So then I do a digital pin low. So that'll turn on that relay for extending the arm. There's a delay on the time, and then it sets it off again. Okay, and then I adjust the current arm, and then Bob's your uncle. So let's see if there's anything else I can show you. Stored the OLED parameters in its own separate header file. Oh, and that's the other nice thing about Arduino coding. It's C, which I'm familiar with, and it makes it really easy to program. So, and then the pin mode numbers I've stored in a separate header file. So if I ever change that, which I don't expect I will, calculate stroke length. These are all helper functions for doing the tracking. So that's pretty much it. I don't know what else I can say about this. It's been fun coding this, and we'll see if this actually works. And here we go.
Right. Well, that went fairly well, the field test. Unfortunately, that was the third field test. The first two tests revealed some issues that I had to resolve first. The first one, which I half expected, was when I plugged the leads in from the linear actuator, it was actually, I had them flipped. So the linear actuator was not retracting back to point east. To get the panel to point east, I had it flipped. So what I simply did was I just took the two leads from the pin 7, pin 8, going into the relay, and just flipped them. And so that resolved it. So this became the retracting relay, and this became the extending relay. That was an easy fix. And so once I did that, I powered it up again, and the relay, instead of retracting the solar panel back to point east, was flickering. So it was turning on off, on, off, on, off. And I had no idea what was causing that, because it was definitely not in the source code. And that one was, that took a long time to resolve and figure out what was going on. Initially, I thought it was due to the fact that I was powering the relay from the Arduino. So I didn't have these. Originally, I wasn't powering it from an external power supply. It was all coming from the Arduino. And so what I did was I removed the ground on this side, and then I plugged this 5 volt to this side. I just basically took this switch off, okay, and then plugged those leads into the V in and the ground, okay. Unfortunately, when I tested that indoors, it was working fine, so it wasn't plugged in to the 12 volt power supply. And it was working fine. It's like, okay, I've got that resolved. So I took it outside on the second field test, and it seemed to work. It was extending, but then in the midday, I was standing there watching it, and it fully retracted. I was like, what's going on here? It fully retracted, and then it re-extended it back to, and pointing where the sun was. And it kept doing that, and it's like, what's going on? That one stumped me, and so I thought, okay, I've resolved it so that it has the relay is using an external power supply. It's not drawing it from the Nano, because each of these relays, and I didn't know this until I started doing some more research on it, draws a maximum of 85 milliamps, okay, which is quite a lot, and this Nano can't support that. And so I'm scratching my head, and then I thought, wait a minute, and I started looking at my adapter. Now, my adapter, original configuration was, here it is. I was using this to power the 12 volt for the linear actuator. Here we go. Okay, so that plugs into the relay, which powers the linear actuator. But on this adapter, there's also a USB port. So I was using this to power up the Arduino, and it was working fine indoors in all my test situation here. But once I took it out into the field and I had everything plugged in, things were going. It was behaving oddly, and lo and behold, it was this guy. So when the relay triggered, or when the linear actuator was triggering it, it was drawing power from this lead, and it was also drawing power from the USB. So 5 volts here and 12 volts here, and I think this was rather unstable, and it caused the Arduino to reset each time. And that was what was causing all of my problems. So once I resolved this, and basically what I did was I no longer plugged the USB cable. I wasn't using this to power the Arduino. I had a separate USB adapter that was powering up the Arduino. And once I did that, everything worked smoothly. So that was a good lesson to learn. Overall, I'm pretty happy with how it works. It still needs to be calibrated a little bit better. I found the tracking was a little bit too fast. It was actually going faster than the sun as it's moving across the sky, and I think it's because I was a little bit. What I think was happening was, even though I measured the speed of the arm in the linear actuator, I had it measured at 4.3 millimeters per second, or I can't remember what it was. It wasn't, when it was in operation, it wasn't tracking the sun exactly, and I think it was due to the fact that the manufacturer specification for the actuator, the speed was 5.7 millimeters per second. That certainly is not true on the one I have. I measured, I think it was 4.3 millimeters per second. And that still wasn't exact. And I think it was due to the fact that the speed is instantaneous when it starts from zero. It has to ramp up. And so what I did was I added, when I'm converting from how much distance I have to extend the arm to a time, I also add a bit of a time offset to that, okay, to address that going from 0 to 4.3 millimeters per second speed. And I was a little more aggressive with it, and I added 0.25 seconds to that, which I think is too much. So I'm going to drop that back down to maybe 100 milliseconds and see how well it tracks the sun. So that may require several iterations before I get it right. But other than that, yeah, I think it works well. One thing though I had noticed, and it is that this clock module, even though it's cheap, and there's a reason why it's cheap, there's a drift to it. It's not exact. So over a long period of time, I can see it drifting maybe 1 minute to 10 minutes over the span of the summer, which is okay. But I'm kind of a stickler, and I'm kind of OCD, and so that kind of bugs me. Yes, I can go and reset the time back so it's synchronized with UTC, every week or every day if I had to, but I don't really want to. And so right now I'm thinking, what if I were to replace this with a GPS module? And and I thought about that, and I thought, you know what? If I had a GPS module, I can actually get the time, because once you get a satellite lock, the satellite's transmitting the time, and it's UTC time, and it's accurate. Okay. Additionally, it's also providing me with latitude, longitude. I only need to get that once, and then I'll just keep that single position. And I'm thinking that might be a better solution. I can just replace the clock module as well as the LED, because I don't really need the LED. I mean, it's just nice to look at, but really, I don't need it. The only concern I have is that a GPS module would use more power or consume more power than what I've got set up here. Now, I have done a bit of research, and Adafruit manufactures a GPS module that they claim uses only 20 milliamps, and I'm kind of leaning on giving that a try. It's a little bit expensive. I think it's $70 on Amazon, so I'm going to see if I can find it cheaper price somewhere else, but we'll see. I may eventually, I probably will, if I decide just order it from Amazon, because they make it so easy. Especially if things don't work, the returns are just smooth. So I may do that, and I kind of like that, because then there's nothing to set. I don't have to set the UTC time. I don't have to replace any batteries. It's just low maintenance, or actually no maintenance. And I can get rid of the pins. I can get rid of the buzzer. Well, I may leave the again, I can reduce the amount of wires here and the amount of gadgets. Don't really need those, right? I mean, I certainly do need to keep the relay and this external power supply, or 5-volt power supply. So, but yeah, the GPS module is a consideration, and I kind of, and the more I think about it, the more I like it. So, and there probably will be a version 2 of this. For now, I still need to package this up. Well, I need to get a PCB, solder all the connections, because this is just a breadboard. This is prototyping. It's not permanent. But yeah, I'd like to solder this into a unit that I can fit into a waterproof enclosure and then mount onto the solar tracker, because this eventually will be outdoors. I mean, I certainly can't leave this out in the open where rain, snow, whatever, because the electronics will it'll just burn out. So I still need to do that. But overall, I'm pretty happy with the tests that have gone over this week. I think we have a success here. Everything works as a proof of concept. It just needs a bit of refinement. So yeah, that's it. I just wanted to share my thoughts with you on this solar tracker project, which was really fun to build, especially coding this Arduino. I really like the Arduino. It's a great microcontroller. The only drawback with this is the limited program space and memory that you have available to code with it, and then also the IDE. It's not. Some things are flaky with it, and I don't know why, but I can live with it, and I can work around those little bugs. So yeah, overall, this has been a really fun project, and I guess I will be off onto the next project.